Okay. Hi everyone. I think we should be live now. Just waiting for confirmation on that. Okay, yeah, it seems like we are live. So yeah, thank you everyone for joining us today. So as a reminder, we are Deep Learning Sessions Portugal, a group of volunteers dedicated to organizing events and sharing insights around deep learning inside and outside of Portugal. So today we'll have we'll have a talk on very exciting recent research. So the format will be as usual. So we'll have around 40 to 45 minutes for the talk, and then 10 to 15 minutes at the end for questions. Although please do place your questions on the YouTube chat throughout the talk, and yeah, I'll be gathering them at the end and asking them to our speaker. So today's speaker is Patrick Fernandes. So Patrick is a dual degree PhD student at Carnegie Mellon University and Instituto Superior Técnico. He is supervised by Graham Newbig and then André Martins. He is also a part-time student researcher at Google Brain. And his main research sort of revolves around understanding how neural networks learn and how they use information to make decisions, with a special emphasis on machine translation. So today he'll be presenting his paper, Scaling Laws for Multilingual Neural Machine Translation, which I believe was just recently accepted at the ICML 2023 conference. So without further ado, please take it away, Patrick.
Thank you. Okay, let me just share the screen. Do you see this full screen? Or I assume yes.
1 second. I think so. Yeah, I think it should be fine.
Cool. All right. Okay. So yeah, thank you for having me. Yeah, I'm going to present the work I've done over the past summer while I was a full-time student researcher at Google. And yeah, this is work that's been accepted to ICML. So yeah, like it should be coming out in the summer. And it's about scaling laws for multilingual neural machine translation. Okay, so recent results have shown that training bigger models on more data is probably the most effective way to improve performance of neural networks in hard tasks. And current state-of-the-art models have many billions of parameters. For example, GPT-3, the example, this is kind of outdated, should be GPT-4, but whatever. GPT-3 figure on the left and Palm on the right are two examples of the power of scale and how it's helped these models be very massively multitask and highly performant. And so given the computation costs of training these large models, there is a growing body of literature on trying to predict their performance as we scale them. So, and as we scale them in terms of both capacity, so the number of parameters, data set size, and compute. So for example, given a certain data set size, what performance can I expect my neural network to have? And if I increase this neural network size, what performance increase can I expect to have? And generally, the way we study this scaling behavior is through the use of scaling laws that quantify the relationship between whatever capacity or data set and performance. And so if we assume, for example, that we have almost infinite data and compute, we can have a functional form, a scaling law that describes the evolution of the loss as we scale the model in this form, where beta is normally known as the model scaling multiplier, and this is task dependent and loss dependent, and higher values mean that small models will have high loss. There's also the scaling exponent, which represents how much benefit we gain from scale, and it interplays with the beta parameter. And lower values mean that we need more scale to effectively nullify beta and reach close to what we deem the irreducible loss. And what we can think about this is like, if we had close to an infinite capacity model, this is the best we could do at the task. And we can think of it as like natural variance in the task, or maybe a limitation of transformers that no matter how big, they'll not be able to capture about this task. And so with these three fits, this describes what's known as a power law relationship. And so increasing model capacity causes a proportional relative decrease in the loss. And a property of this scaling law of this form is that if we plot it in the log-log domain, it follows a linear relationship, which is highlighted by the picture on the right. So on the right, the line is a fitted scaling law based on a couple of early points. So earlier in the, where is it? Sorry. Do you see my mouse? Yes, no? No, maybe not. Okay. But yeah, so on the top points of the earlier points in the curve were used to fit this law, and then the line describes the predicted performance, while the other points describes the actual performance of training these models. And so we can see that the scaling laws of this form are able to describe the performance of, in this case, was GPT-3 style model. I think it was language modeling, and many of the works have shown that the scaling laws can describe the performance of neural networks in many tasking domains. So, for example, recent work has shown that the performance of empty models also follows the power law of scaling. There's some caveats. So, for example, encoders and decoders scale differently, and they have different scaling exponents. But overall, the scaling properties are very similar, and they're still captured by this power law functional form. And follow-up work has also found that similar scaling properties for scaling according to training set size, and also when scaling with different architectures. And as I said, one important property of these scaling laws is that they allow us to predict the performance of large models that we're planning to train. For example, we're trying to train models for English-German. We can predict how good we'll get at English-German without actually training the very large models, assuming that we train a subset of smaller models that we can use to fit our scaling law. First, maybe, I don't know, are we doing interactive questions, or should I just take them all at the end?
Yeah, I think the plan is for you to take them all at the end. Sorry.
Okay, yeah. Okay. No worries, yeah. Okay, so previous work has mostly considered scaling laws for a single language task. And so one important capability that highly benefits from scale is multilinguality. So the ability to solve a task in multiple languages. And this is very crucial to breaking the language barrier in NLP, because a lot of the low resource languages don't have enough data. And having multilingual models that leverage transfer from high resources is very important to have technologies that work for low resource languages. And so we want our models to be able to solve tasks in multiple languages, and ideally multiple tasks as well. And so, but there are challenges in developing massive models that current scaling laws don't help, in particular multilingual massive models. So one important question when we're trying to train a multilingual model is, how should I weight the language in the training set? So let's say I'm training a model on hundreds of language pairs. Should I sample from each language pair with the same probability? Or should I sample proportional to the language's dataset size? And the important question is, how will this affect the performance on the individual languages that the model is able to support? And the current scaling laws don't say anything. They just say, here's the whole loss across the whole test set, which can be your multitask setup. So you don't know how this will affect the performance on individual tasks. And this is compounded by the fact that we cannot easily do hyperparameter optimizations with hundreds or tens or hundreds of billions of parameters. So we're mostly limited to making a choice and sticking with it. And so the question that we ask in this paper is, can we empirically derive scaling laws for the multitask multilingual models that predict their performance for any weighting of the language in the training set? For example, can I have a single scaling law that predicts the performance of multilingual models at multiple scales, trained with either 50% weight on German or 50% weight on Chinese, as well as the performance of the same model trained with 90% of weight on German and 10% weight on Chinese? And how will this affect performance on the individual languages? So this is the goal that we want. And as a background, maybe important background to understand the work is what is multitask optimization. And so suppose we want to train a model for with parameters theta for k tasks, where we can think of tasks here, in the case of our work, as different language pairs. So we can consider translating from English to German as a task, and translating from English to Chinese as another task. And we want to train a model that does both, basically, right? And we can define this multitask optimization. We first have to have a loss for each task. So, for example, your cross entropy on the individual language pairs. And multitask models are often trained by minimizing what's called the scalarized loss, which is if we define an a priori weight for our tasks, we just minimize the convex combination of the losses on these tasks, where the weight of each task is something that we define a priori. So for example, if we care 90% about German 10%, we just say 0.9 on German and 0.1 on Chinese. And recent work has shown that scalarization performs on par or better than more complex multitask optimizers. So rather than doing the scalar loss, you could use very fancy multitask optimizers. But recent work has shown that like just training scalar laws, you're going to get probably better performance by choosing rightly the W than if you do multitask optimizers. So we say that scalarization is Pareto optimal compared to other multitask optimizers. And importantly, also, scalarization is typically implemented implicitly. So rather than doing a forward pass with both English German and English Chinese, and then weighting the losses, where you take advantage of stochastic gradient descent, and instead you sample from each of the language pairs proportionally to the weight of the loss. So if you have 90% on German, 10% Chinese, 90% of the samples that the model will see will be from English German, 10% will be from English Chinese, basically. Cool. And okay, cool. And so one important fact about multitask optimization is that in the presence of sufficient data for each task, there will be a performance trade-off frontier where training a model on one language pair will necessarily degrade the performance on the other language pair. And the best we could do is to get the best performance on that language pair would be just to train on that language. So in this figure, this is an example. If we consider the top left corner, this is the best model you can get for task 1, and it will be just by training on that task. And on the bottom right corner, the best model you can get on task 2 just by training on that task. And by training on some mixture of these tasks, all you can do is some point on this Pareto curve. So there will be a trade-off between both tasks. And this is normally the regime that models in high resource languages are, because if we have enough data for a language, normally the best you can do in terms of an empty system is just training on that language. So this will be the case for languages like English Chinese, English German. And so importantly, we restrict the scope of our work and we consider, can we empirically derive scaling laws for multilingual models in this data-rich scenario? So this is a simplification of the problem, but it's something we study preliminary, just to simplify our analysis, because that means we don't have to consider data terms in the scaling laws. Cool. So yeah, so we attempt to first fully understand this data-rich scenario. To do this, we train models for 3 language pair combinations: English to German Chinese, English to German and French, and German Chinese to English. So all of these models are models trained for 2 tasks. And we train on 600 million sentences of production data for each language pair. So each model of these 3 models, or 3 model classes, is trained with 1.2 billion sentences. And we train up to 8 model sizes, ranging from 10 million parameters to 1 billion parameters. And importantly, we consider non-embedding parameters, which is what people consider in the scaling law. So when you see this L of n, this is with respect to non-embedding parameters. And it's an example where we show like the sizes of the models. I don't know if this is big enough, but you should be able to see it. And yeah, and then importantly, this is important to understand, for each of these models, we vary the task weight probability for each of the languages or language pairs. So to give an example, for English to German and Chinese, we train 10 tiny models, where we train a tiny model just on German, a tiny model on 10% of German, 90% German, 10% Chinese, in this case, 1% German, 99% Chinese. Then we train a model with 0.05 German and 95% Chinese, blah, blah, until we train a model with just Chinese. And this means that we train a lot of models, but just to clarify, for every model size, we train a different model for each of these task weightings, right? And then we evaluate our model both in-domain and out-of-domain test sets. So when deriving our scaling laws, we derive scaling laws for both the in-domain case and for out-of-domain to see that our findings are not just a property of some form of overfitting or something like this. Cool. So we start by just fitting individual scaling laws for each task weighting. So for example, for the setup where we train on 90% Chinese, 10% German, we fit a scaling law for this task weighting, right? And this is nothing new. So this is nothing that we expect to see new. This is just what people have done previously in some sense. It's like considering the combination of tasks as a single task. And then we try to analyze what, we do this with its scaling laws, and we see that, as expected, a parallel-like scaling law is able to accurately predict the performance of very large models. And first of all, note that the large model here wasn't used to derive the scaling law. You see that the marker is slightly different. So it means that this model, the earlier points were used to fit the scaling law, and the last models were used just to verify the prediction of the scaling law, right? And we see, but this is nothing new. We expected, we know that scaling laws predict the behavior of these models. But interestingly, when we start analyzing the scaling laws, we see some invariances. So here we plot the fitted coefficients of the scaling law. Remember the form on the top. And this is a coefficient, each of the coefficients, one value for each task feature, right? And the shaded areas mark one standard deviation of uncertainty, which we computed with parametric bootstrapping. And what we see here is that there seems to be, while the model multiplier varies, so like as we increase the task weight, it goes down as expected, the scaling exponent and irreducible loss seem to be mostly constant across the task measure probability, right? So in other words, what this means is that a model trained on 10% German or 90% German could benefits the same from scale, because they will, like in terms of the power law, they'll scale the same way. And I'll go a bit more about the implications of this later, but this is something that a priori wouldn't have to be the case. It's something we observe empirically, is that they seem to have the same scaling exponent and irreducible loss across task weights. And so, like if we subtract this irreducible loss and we plot the log-log axis, this is symbolized by the fact that all of these lines are parallel to each other. So on the log-log domain, they're just parallel, and they're still able to predict performance well. As this is the same law as before, no different law. You just plot on log-log domain. And we also find that the same thing holds for different domains, with slight variations, right? So we get the same if we derive scaling laws of the performance of our models on, like in this case, new test, which is a standard test set for WMT. We see that the same behavior of like the multiplier goes down, but the rest remains approximately constant, right? So based on this finding, and we also found that this holds for different language pair combinations as well. So we see that for English, German, English, French, we see the same behavior happening. Cool. So based on these findings, we make and this is an assumption that we make. So we didn't run a test to verify that, truthfully, this is their scaling coefficients. Like generally, this is an empirical science. And so what we do is we make the assumption that the scaling exponents and irreducible loss are independent of the task weight, right? Because as we saw, they're mostly independent, so we can make this assumption. And what this means is that then we can derive a joint scaling law for all task weights, right? Where we have the same exponent and irreducible loss for all task weights, but different multipliers for each. And what we do practically is that rather than fitting individually the scaling laws for each of the task weights, we take all the empirical points and we fit the joint scaling law with all these observations that fits all of these coefficients at the same time, right? And this means that we have way less coefficients to fit. So we're probably also going to need less models to fit an accurate scaling law. And it's like a property of statistics in general, right? And so what we found is that despite the significant decrease in the number of total fitted parameters, our joint scaling law is still able to mostly capture the scaling behavior. So there's still some anomalies. For example, you see that like the models with very low task weight seem to deviate a bit more from this joint law, but we have some hypotheses. For example, if we have very low task probability, that means that you're going to see very little samples from that task. So you probably need a lot more steps to be able to converge on that task. So we suspect that for these models on the top left and on the top right, is that they're just a bit underfitted. And if we train them for many more steps, they might be able to reach something that's more closer to the scaling law, despite the fact that it's still very close to the scaling law. But yeah, so it's still a very good fit. That's my point. And the interesting thing is that if we have this joint scaling exponent loss, we can ask how large should the model trained on both German and French be to match one trained on only German. So for example, let's say we have the scaling curves, and the red scaling curve represents the performance on German for a model trained on 50% German, 50% French, or Chinese, I don't remember. In this case, Chinese, sorry, this is wrong. And the blue scaling law represents the model trained on only German. So this is the performance of the model trained on only German. So what we can say is, like, for example, let's say I'm trying to aim for this loss, right? And this would be achieved by a model just trained on German with n effective parameters. So we can write this equation to say, okay, how many parameters would be needed for a model trained with German and French to reach the same performance of this model just trained on German? And so this is symbolized by this equation, right? So what is the number of parameters we call the number of effective parameters allocated for that task, right? And one property of having this joint scaling law and exponent is that if you write the math, turns out that you can derive this empirically by the regress methods that you have. Basically, if you write down the equations, you arrive at an equation that tells you that your rate effective parameters is given by the ratios, like this exponential ratio of the betas, right? And so, and what this also means, I think this is an important consideration to have, is that if you move m to the other side, right, and you have this, what we call effective parameter ratio, right? So it's the ratio of number of effective parameters over the number of parameters. An important observation of this is that, like, it's independent of the capacity. So you'll see that if you move n to the left, there'll be no parameters on the right side. So this means that even if you have a model with 100 million parameters on English, German, and English, French, and they have a model with 100 billion parameters on English, German, and French, they'll have the same effective number of parameters allocated, or effective number of ratio of parameters allocated to the same task. And this is an important property, because some people might have this intuition that, like, the model might have more transfer if you scale. But what this means is, no, there's no more transfer. They still allocate effectively the same number of parameters to each task. And again, this is, in insight, might be maybe some obvious, but, like, this is not obvious at all a priori. And so this is a curious finding that we found. And if we have this, it means that now we can study what we call the capacity splitting behavior of the model. So, for example, we can check, okay, how is the model splitting the parameters according to the languages, for example, for English, German, Chinese, as we change the task weight. And what we observe for this case is that, like, the effective parameter reduction is almost linear on task probability. So that means that a model trained on 50% German is very close to a model trained on only German with 50% of parameters. So this is not exactly true. So there's a small variation, right? So there is some gain, but it's maybe less close than most people think. It means that, like, you're not gaining that much parameters from, like, doing multitasking for this task. And this might explain a lot of the findings that we have, that multitask models on data-rich scenarios generally don't outperform single task models, right? At least for, and this is in the English into German, English into Chinese, right? And this is also seems to be mostly invariant to in-domain and out-of-domain test sets. So it seems to be more of behavior of these language pairs, or at least this task. And you might ask, oh, maybe this is just a behavior because German and Chinese are not very close to each other, right? So therefore, maybe that's why they don't share the parameters, right? Maybe some more closer language would do it, right? But that's not the case. What we found is that, like, so conventional wisdom MT would say, yeah, sure, French would have more positive interaction and therefore should share more parameters. And some intuitions of, like, they have more aligned representations or something like this. But what we found is that, no, despite being more similar, capacity splitting for English, German, French is very similar to English, German, Chinese. So there seems to be very little sharing of parameters between these language pairs, right? And so, but importantly, okay, but while different languages, like having more closer language on this direction doesn't seem to matter, we did find that, like, we compared interactions between tasks when translating out of English and versus translating into English. So in this case, it would be the case of your two tasks are in the encoder side versus your two tasks are more on the decoder side, right? And in this case, we found that now, in contrast, direction plays an important role in effective capacity splitting. So there seems to be much more positive synergy between tasks and higher parameter sharing when you're doing the multitask on the encoder side. And it's unclear if this energy arises from having just English as a target side. I suspect that multitasking coding is intrinsically more amenable to parameter sharing, because it's just generating language in generating text into different languages is a much harder task than encoding language, and therefore my intuition is that it's also easier to share parameters in that case, if that makes sense. But again, intuition is not proven; it's just more like an empirical science. Cool. And now finally we ask, can we leverage our multilingual multitask scaling law to guide task balancing in large models? So remember the previous equation about the ratio, right? So like we can reframe them rather than being n effective as in the n times the effective parameter ratio, right? Where we define the effective parameter based on the betas, right? But in the current form, we can only predict performance for the weightings that we use to fit the scaling law. So for example, I showed you these values of 0.05, 0.1, 0.2. If we wanted to predict performance, because we need these betas for the joint scaling law, we could only predict performance for the weightings that we train models for, right? So if you were asking, oh, but what about 0.045 German and 0.055 German, Chinese? Our current scaling law would not be able to tell you that, right? But what we can instead do is we can, to extend to unseen task weightings, we can instead focus on estimating this ratio function, right? So we just parameterize in some way, some fit coefficients. And this is like, I think this is, when we did it was based on like the Bernoulli equations or something like this, which like based on the figures, right? And what we can do is we can just fit these coefficients as we would fit the other parameters of the scaling law. So you just replace them in the scaling law and fit them as we would fit the betas and everything else, right? And if we do this, we can now predict performance for any task weighting. We can train on whatever, the same task weighting before, but now rather than having betas, we'll have this parametric f, and now we can use this f to predict performance on any task weighting, right? And given this, what we found is that like this almost perfectly captures the full task performance frontier across a variety of model scales. So on the left, we see the same plots as before, but now with our predicted function approximator, ratio approximation. And on the right, we show the Pareto frontiers. And importantly, the Pareto frontiers is something that our scaling law predicts. So the dotted lines are all predicted by the derivative scaling law, right? And the points are the empirical points from training models. And with access to such accurate predictions of the performance frontier, a practitioner can precisely determine how should they weight their individual tasks to achieve whatever trade-off they want on their performance loss, whatever they want. And the choice of function of class, in this case, we chose to use as f this class of functions, which has 3 coefficients, right? And this is highly dependent on the practitioner's use case or computational budget. So in our case, we prioritize accuracy. So we train a lot of task weightings and a lot of models to have a more accurate fit, right? And this provides to have a more accurate function like ratio approximator. But we also found out we can have quite good accurate predictions with just a very simple linear model, where we just have to fit one coefficient for the function approximator. Yeah, of course, it doesn't capture the same behavior, right? But it still provides quite decent Pareto frontier predictions, right? So yeah, this is like, this is not easily done. Like, I just want to highlight, this is generally very hard to predict. And I do believe that the reason we did it in this case with such good predictions is because we consider the high resource case. But this is quite novel and quite useful, I would say, in general. It just requires training a couple models. And to show also that, like, up until now, we've been doing most of our analysis with cross entropy, so the actual test loss, right? And so in machine translation, people use metrics like BLEURT, ChrF, BLEURT, comment. And importantly, these metrics also take into account the decoding problem. So, your model might have good test loss and cross entropy, but when you decode, it might produce not very good samples. And importantly, likelihood, even if it has high likelihood the sample from a model, they might not even then correlate well with human preferences, right? So to alleviate the concerns and practical applicability of results, we repeat all our analysis by using as a loss ChrF and BLEURT. And we obtain translation from the model using beam search, basically, right? And first, we see that ChrF generally has an almost linear relationship with perplexity, right? So the practical application means that then it means that our scaling law is also able to capture this trade-off frontier quite well, right? So this is a practical application. If you wanted to aim for a particular ChrF for your models, you could do it with our scaling laws. And we have very similar BLEURT findings for out-of-domain test sets. So we already see that they don't correlate as perfectly, but despite that, our joint scaling law is still able to have quite decent trade-off, like trade-off frontier predictions. Yeah, and so this means that, for example, while you could argue ChrF is not maybe very informative because it doesn't correlate that well with human quality, BLEURT is state-of-the-art metrics for translation quality, and they correlate decently well. So this means that like, you could theoretically aim for a precise trade-off in quality for your translations, because you just would pick a BLEURT value and pick the trade-off that you want, basically. Cool. So yeah, I went kind of fast, but I think I have the conclusion now. So yeah, in this work, we studied the scaling behavior of multilingual models in the interference scenario, which is surprisingly simple. It has almost constant scaling independent of task weight. Language and task similarity play a limited role, at least for out of English. But the into English direction, or in this case, the direction of the translation, seems to matter a lot for parameter sharing. And as future work, we plan to investigate multitask optimization for more diverse tasks. For example, something very hot right now is to train language models with a combination of like natural language modeling and code modeling. And there's questions of, for example, how do these objectives interplay with each other? What's the transfer from like code to natural language? And this is something that we are and kind of were, I'll discuss maybe this more at the end, to study. And also, I think very important for the practical applicability of these results is to try to see, okay, what happens when you don't have infinite data? Like, and at what point does transfer happen? And at what point can you get a model that outperforms your models just trained on that single language pair, right? So I think this is probably one of the most immediate things to have much more wide practical application, because this means you could directly select what languages do you want to use to maximize, for example, the performance on your low resource languages. Yeah, and this is mostly what I have. I have 2 more slides I want to show since I have time. First, we also show that like we derive, for example, you might ask, oh, maybe this is a scenario that you showed for 2 tasks because you only studied the case where you have 2 tasks, right? But we have preliminary results in the appendix that show if you use your joint scaling laws that you fitted for your 2 tasks, right? In this case, for English, German, Chinese, and English, German, French, and you use this scaling laws for your English, German for predicting this trilingual model, right? This scaling law that was used on the duolingual model, called duolingual, is still quite accurate to predict the performance evolution of this trilingual model, because you can still use the same task weight on German and use the scaling law. And you show that this, with this, like, how do I say, you can do like almost a greedy search for the because it's much harder to analyze the multidimensional case, because you cannot tractably explore the whole task space, right? Because we trivially explore it, because when you have a binary case, one is just minus the other. But with n t bigger than 2, now we have a combinatorial explosion of the exploration, right? And so what this hints is that we can explore this very multitask scenario by exploring just the 2 languages, the combination of 2 languages or 2 tasks that you might have. And another thing is that there's already seemed to be some follow-up work to this work. I think it was released like in 2 weeks ago. You know, they explored like the Pareto frontiers and analyzed also the low resource case, or the data limited case. And they showed, for example, here that you are able to break the Pareto frontier if you now start studying low resource, and it's no longer a Pareto frontier, but now there's an optimal point that exists, basically. Cool. That's mostly what I had.
Awesome. Yeah, thank you very much, Patrick, for a super interesting talk. There's some questions in the chat. I have some questions myself, but I'll start with the ones in the chat. So the last one by Manuel Madeira is, are there any theoretical results that supports this sort of empirical power law findings that you have?
Like most thing in deep learning, no. So this is more purely an empirical finding. And honestly, my opinion, I have mixed doubts about this. There's a paper that's called Broken Scaling Laws, which like proposes a weird form of scaling law that you might think, oh, that's just funky, but then it outperforms the traditional scaling laws. So it might put you wonder, okay, then what are these scaling laws actually meaning, right? But I generally am an empiricist, an instrumentalist, and I believe that's our best hope to get any kind of science in deep learning, because they're starting to become too emergent to analyze theoretically. And so, no, we don't have theoretical results for this, but like I think the best thing we can do is be instrumentalists and treat this as like a natural phenomena in the same way that we treat physics, right? We don't try sometimes to derive laws for physics. Sometimes from the ground up, we come up with theories and we verify them experimentally. And I think, at least from what I got from this project, that this seems to be one of our most promising approaches to this kind of science of deep learning, because you can argue that like, yeah, there's no theoretical justification, but you cannot argue with the practical implications of having something like this. If that answers the question, yeah.
Yeah, for sure. That makes a lot of sense. So next question, also by Manuel, is it possible to predict these scaling beta constants a priori?
So because of the fact that they're not theoretically derived, they're just an empirical observation, you have to treat them like the constants of the universe, if you want, right? And so you can try to, like, that's what we do, right? Like, that's kind of what we do when we have this here. We're predicting the betas, right? Because by predicting the function approximator, we're implicitly predicting the betas, or at least the ratio of betas, right? But from the scratch, without having anything, it will be very hard, because it's very much these betas. And so, for example, like, I assume, like, if it's just about the betas, I would argue that yes, but generally predicting the scaling coefficients, no, because they're very much a property of, the task, the model. You'll have maybe different exponents if you change the domains. So, like, I would say no. Like, the whole point is that they're derived empirically, just like the constants. It's like, can you derive the constants of the universe a priori? Some of them, but most of them, they just exist, basically, if that makes sense.
Yeah, that makes a lot of sense. I like the physical analogy. So another question by Manuel is there any intuition supporting this performance trade-off frontier? I think this refers to a plot that you had at the beginning.
At the beginning and here as well, I guess, because this is also a trade-off frontier.
Yeah. So why does this happen?
So there's a paper. This started on our work. I think I can show it here. I recommend reading this paper here, but there's a lot of work on this. Where is it? Here, this paper at the bottom, which analyzes precisely like the data-rich scenario, and there's like the previous, almost the predecessor work to this one, basically. And so my intuition here would be like, I have an even bolder intuition, because yes, there could be a trade-off frontier, right? But I have an even bolder intuition is like, okay, what predicts something? Again, take this, we're getting to the speculative realm, so like, don't quote me much later. But what would predict something like this linear profile of like the capacity splitting? And I'll make the statement that like, in the case of infinite data, truly infinite data, the best you can do with the truly infinite representative data of your domain, your task, my intuition is that the best you can do, and I'll also argue this, like in the convex case, it's like, I'll say this, in the convex case, it's proven that this is all the best you can do. So if you want some theoretical intuitions, the convex case, you can prove it, basically. That the best you can do in the convex case is to have a trade-off, right? Now, you can argue maybe in the non-convex case, there would be something, even in the data-rich scenario, that like creates a non-convexity, right? But my intuition here is that like, on the limit of data, right, the best you could do is just train on a task. Why would the other task help? Right? Like, the task is not going to be the same task. And rather than getting a new point for your auxiliary task, just get a new point for the actual task, right? Why would the auxiliary task help? The only reason I can see it is for some optimization trick. But if you have infinite data, you don't have to do optimization tricks. You're literally fitting the distribution, right? And so, like, and assuming that there's not, like, it matches the test distribution, there's also no problems of overfitting, because you cannot overfit infinite training data, right? And so if this intuition is like on the limit, you cannot do better than just training on your task. And the intuition here is that on the limit, I'll give you this, if you truly had infinite data, this curve would start degenerating towards the exactly y equals x, because we don't have truly infinite data, right? We have like, I don't know, a billion sentences or whatever. My suspicion is that on the truly infinite case, this would degenerate to just the y equals x. And bolder statement here is that you see this reverse line, right? The one for the reverse direction. That one, even given more data, rather than 1 billion, maybe 100 billion, or maybe 1 trillion, it would also start to degenerate towards the y equals x line. if that intuition makes sense. So what I'm saying is this deviation from this, but this is an intuition, not proven. So take it a grain of salt. Is that if you got what all this data does is starts putting this curve, bends the curve to start become like this. And one of the intuitions that we had, if we were to go for the data scaling laws, is could the data term explain the bending of this curve, basically? So if you add more data, maybe this would be on the equations expressed by, like, if you start deriving scale laws, expressed by less curvature on this law, on this part, to the point that eventually it starts becoming a trade-off and starts becoming like a non-Pareto curve, basically. But again, intuition is very careful what I'm saying here. If that makes sense. Sorry, I started waving hands.
That makes perfect sense. Yeah. Thanks for the answer. A question that I had, also sort of related to intuition, was whether you can give some intuition behind this heuristic fact that you found that language similarity seems to have little impact on the scaling laws. So that does feel counterintuitive.
Yeah, it is counterintuitive. So for example, I would not, again, my intuition here is that it plays a lot with the data role here, right? And so encoder versus decoder have a lot more amenability to share. Like encoders seem to have more amenability to sharing. And I think one experiment that we didn't include in the paper, but I think I have preliminary results somewhere, is that, like, if we do the reverse direction, but for German French, right, rather than German Chinese. So here, if you plot another curve, then this curve would no longer be exactly like the other one, but would be, this one you could tell would be slightly up. Like, so the bending regard to the blue point would be even higher than the blue and green points on the right curve, right? Mm-hmm. So it seems that, like, for the reverse direction, task similarity does play a role, right? So the way I frame this intuition is like task similarity plays a role only when you get into this data limited regime. And you get into this data limited regime depending on how close the tasks are, right? So again, very intuitive, I have no proof to this claim, so don't cite me later. But my intuition here is that, like, the closer your tasks are, right, the higher the number of samples you need to enter this data-rich regime. So if two tasks are very similar, it means they can benefit from transfer up to trillions of sentences. If they're more dissimilar, then up to 1 billion, they start becoming beneficial to each other. But maybe, for example, on the English-German in the second plot that you see here, right, maybe if we did 1 million sentences, this would not be the curve. And the curve would already show that, like, German French benefits more than German Chinese, if that makes sense. Yes. But again, the way to verify this would be to actually run the full data scaling laws for this, basically, which we never fully did, yeah. But my intuition would be that, like, the reason that you don't see is that they're starting to, on this direction, they're starting to end up this data infinite, close to this infinite data regime, and therefore, even if the languages are similar, there's transfer is almost playing no role, if it makes sense.
I see. Yeah.
Or at least it doesn't play as much as a role as, like, the English side of things or something like that.
As usual, yeah. Definitely, yeah. Feels strange, but yeah, I see the intuition.
But this is how it's shifting when I start getting this, like, what is capacity is independent of model size, right? Like, why is this the case? It feels like it can only be on the data side, right? It cannot be on the capacity or anything like this.
Yeah, for sure. So another thing that I wanted to ask is, and I think you briefly mentioned this at the end, is can you give some examples of sort of other potential lines of research surrounding scaling laws for other multitask setups than multilingual translation?
I mean, model. Just like you can consider, like, pre-training your language model and then doing evaluation of the language model on individual benchmarks, right? As exactly the same problem, because your pre-training data for these multilingual models is implicitly a multitask problem. Like, when you do next word prediction, you're doing, depending on where you get your data, you're doing a different variation of this multitask problem, right? So what you could do explicitly is, for example, for code and natural language, these are normally very explicit. You collect your data for code, or you collect your data for natural language, and you merge them and do all of this together, right? But what you could do is instead explicitly separate them and then analyze, okay, how much benefit is code actually giving me for natural language prediction? Because, sure, code helps for code generation, but a lot of the arguments that people have seen, especially with GPT 3.5, is that, like, part of the code pre-training objective seems to be helping with, like, reasoning abilities, right? There's this intuition that people say that, like, part of the reasoning abilities and the math reasoning abilities comes from the code generation. And this would allow you precisely to say, in terms of the natural language part of it, how much is code helping with this? And can I, by increasing my code data, improve like reasoning ability skills in natural language? So I can see this as a very practical use of this scaling law paradigm. So you could tell it, for example, okay, I want this model to get better at reasoning, but I have no more natural language data. I need to put more 100 million sentences of of code, and I need the model to be this much bigger, because to compensate for the capacity splitting or something like this.
Yeah, that's a very cool application, and I guess that's something you are exploring.
No, I'm not working on this at the moment. So if someone wants to take it, my boss left to OpenAI, so this I'm working on this. Yeah,
it's good to go then. Okay, so one last question maybe is whether again you can give some intuition behind this sort of experimental fact that you found that there's this invariance phenomenon on the scaling exponents. Is there any intuition at all for that? Any theoretical reasoning, maybe?
I mean, the theoretical reasoning seems to be, theoretically, no, as I said, right?
Yeah, that's it.
But my intuition simply, like, the way I'm framing my mind around this is that, like, though you can reframe, I like the reframing as the scaling exponent is the same. I like to think a bit, I think it's easier to think conceptually about this statement here. Because that's the implication of this scaling exponent.
Yeah.
And what this is telling, the implication seems to be that, like, the way languages, the models do multitasking has nothing to do with how big they are. At least in this data-rich scenario. Again, it could change that, like, this is not the case for data-limited scenario. But when you have infinite data, it doesn't matter how big it is, the model will have to split its capacity, right? And even if it's 100 billion or like 1 billion, right? And this seems to be what happens, not like theoretically, it seems to be like models split their capacity independent of how big they are. So it seems to be more of a property of the problem itself than the neural network itself, if that makes sense.
Yeah, it does. Yeah.
And the property of this implies that the scaling law is then constant, basically.
Agree. Yeah. Yeah. Thank you very much. That was great, Patrick. I don't think there's any more questions, so I just want to quickly mention a couple of things. So first, that the video for this talk will be available on our YouTube channel. So please do go check us out and subscribe there for future events. And similarly, the slides will be available on our GitHub page, and the link for those should be in our website, which you can find the link for in the description of this YouTube video. And finally, I would also ask if you have a bit of time to please fill in the feedback form for this talk, which is also in the description of the YouTube video. So that really helps us to plan the best possible talks for the future. And I think that's it from our side. So yeah, thank you everyone for joining. Thank you, Patrick, for a really great talk. And please be on the lookout for future events by us. So we have a couple of things in the oven being planned for the next few months. So yeah, be on the lookout for those. So thank you.